Graphical representation of complex number. A complex number can be represented in Cartesian form, polar form, trigonometrical form, or the exponential form. We have discussed that complex number z is x plus iy, where x is the real part of the complex number and y is the imaginary part of the complex number z. So we can write z equal to real part of z plus I into imaginary part of z. We have introduced two terms, that is the modulus of the complex number. It is equal to square root of x square plus y square. That is, it is the square root of the square of real part of the complex number plus square of the imaginary part of the complex number. And other term is the conjugate of the complex number. It is equal to x minus iy if z equal to x plus iy, and it is obtained when we replace I with minus I. Graphically, any complex number can be represented as a point in the complex plane which is formed by the two mutually perpendicular axes. Here we have taken two mutually perpendicular axes. The horizontal axis is the real axis and vertical axis is the imaginary axis. And complex number is z, which is x plus iy. So this complex number can be represented by a point which is having the coordinates xy. This is the ordered pair for the complex number, in which first is representing the real part of the complex number and second number is representing the imaginary part of the complex number. So if we take a point P which has ordered pair xy, it means that distance of the point from the origin which have the ordered pair 0 0 have the distance x along the real axis, and the point P have the distance y along the imaginary axis. On this graph, we can represent the modulus of the complex number and the conjugate of the complex number. We have taken that the complex number is z equal to x plus iy, which can be written in the ordered pair as x comma y, where first part is showing the real part of the complex number and second is the imaginary part. The modulus of the complex number is the square root of x square plus y square, which is represented by the distance between the origin and the point. So this distance is mod z. Also, the conjugate of the complex number is x minus iy. In ordered pair, we can write it as x minus y. If we draw this point on the graph, the ordered pair shows the distance on the real axis is x and distance on the imaginary axis is minus y. So this point shows minus y. Therefore, the conjugate of the complex number is say p dash, and it has the ordered pair x comma minus y. So we can say that the conjugate is the image of the point p about the real axis. It is the image of complex number z about real axis. As we have discussed that a complex number in Cartesian form can be written as x plus iy, and any complex number can be represented as a point on the complex plane, and we can write it as in the ordered pair of the real and imaginary parts. If we draw this graphically, real axis is the horizontal axis and imaginary axis is vertical axis. Complex number z is represented as a point on the complex plane, and the distance of the point P from the origin is the modulus of the complex number, and its image about the real axis is the conjugate of the complex number. This point P, which is representing a complex number on the complex plane, can be written in terms of the polar coordinates, that is the ordered pair of the r and theta. Here r is the modulus of the complex number, where theta is the argument of the complex number, or we also call amplitude of the complex number. Suppose these are the two mutually perpendicular axes x and y, and on this a point P is representing the complex number having the ordered pair r, which is representing the modulus, and theta, which is representing the argument. So this distance of the point P from the origin is representing the r, or the modulus of the complex number, and theta with positive x-axis, this is the positive x-axis, is the argument of the complex number. If we drop the perpendicular from point P on the x-axis and y-axis, and distance of the foot of perpendicular from the origin is say x along the x-axis and y along the y-axis, then we can write that modulus of the complex number is r, which is equal to square root of x square plus y square. Similarly, argument of complex number z can be written as 2n pi plus tan inverse, and because tan theta is perpendicular by base and perpendicular is y and base is x, so theta will be equal to tan inverse y by x. So it is tan inverse y by x. There are the infinite possible values for the argument for because n belongs to set of integers. For a particular value of argument, that is the theta lie between minus pi to pi, we get the principal argument, and it is written as argument of complex number z equal to tan inverse y by x. From the graph, we can see that if the point P representing the complex number z lie on positive x-axis, that is, this is the graph, this is the x-axis, y-axis, and point lie on the positive x-axis. So measuring the angle from the positive x-axis to the point, this angle represents 0 degree. If it is lie on minus x-axis, that is, this is the graph, x-axis, y-axis, and points lie here, then it is having the plus pi angle. Direction taken anti-clockwise is taken positive. So it is theta equal to pi. If point P lie on plus y-axis, in that case, the graph will be, this is the x-axis, y-axis, point lie on the y-axis. So we have to move anti-clockwise by 90 degree. So it is again taken positive. But if the point lie on the minus y-axis, in that case, if we draw the graph, this is the x-axis, y-axis, and point lie on the minus y-axis. In this case, we have to move clockwise by 90 degree. So angle is, or the argument of the complex number is minus pi by 2. In trigonometrical representation, suppose complex number z is x plus iy, and it can be written in ordered pair as x comma y in Cartesian form and r theta in the polar form. If we draw the two mutually perpendicular axes in the complex plane, this is the x-axis or the real axis, and vertical axis is the y-axis or the imaginary axis. There is a point P which is representing the complex number z, and the distance of the point P from the origin is the modulus of the complex number, and it is also the r. And the angle of the OP from the positive x-axis is theta in anti-clockwise direction. So it is taken positive. Therefore, if we draw the perpendicular from the point on the x and y axis, the distance of the perpendicular from the origin is suppose x in x direction and y is along the y direction. Therefore, we can write that x equal to r cos theta and y equal to r sin theta. Therefore, this z can be written as x plus iy, or replacing x and y we have r cos theta plus I r sin theta, or simply we can write it as r into cos theta plus I sin theta. Here r is the modulus of the complex number and its value is root x square plus y square, and theta is the argument of the complex number or the amplitude of the complex number, and its value, that is the principal argument, is given as tan inverse y by x using the equation number 1 and 2. That is, if we divide equation 2 by 1, we will have y by x equal to r sin theta by r cos theta. R and r get cancelled, so it is simply tan theta. Therefore, theta is equal to tan inverse y by x, which is the argument of the complex number. A complex number having the modulus r and argument theta can be represented into the exponential form. Here we have taken the complex number as z equal to x plus iy, and in trigonometrical form we have written it is r cos theta plus I into r sin theta. So it is equal to r into cos theta plus I sin theta. Using the Euler's theorem, which says that ei theta equal to cos theta plus I sin theta. So we can write z is equal to r into e raised to the power I theta. This is the exponential form of the complex number, where r is the modulus of the complex number given by root x square plus y square, and theta is the argument of the complex number, and in as a principal argument its value is tan inverse y by x.